Oh, yes. Top 5. The option just in case I
What? No. Right, yeah, I was saying we need it. Nothing in this place, right, dude.
We'll give you the time. We will take into account the time. Come on, Jamie, put some elbow into it.
oh.
The floor is yours.
All right.
So today I get to introduce a new chairman, Chairman of Ramsky.
Wrong this session with a roll of eyes. Our first speaker is Julia.
Who's giving her first ever talk.
Wow.
Okay. So, I'm going to give an introduction to topological quantum computing and quantum groups, or representation theory of quantum groups. And I'll explain what that is. My hope is to explain what that is to some extent. Okay, so the basic idea behind topological computing is to exploit topological properties to make implementation of quantum gates robust against small errors, so against deformation. So what that means is if we could actually do topological computing, then it would be much easier to implement quantum gates. Okay. So our basic physical setup, in very broad terms, because I don't know very much physics, is we have some quasi-particles called anyons on some two-dimensional surface. So, say it's here. There are some operations that we can perform on them. So we can exchange them. So I could do this, or maybe do that, and I can fuse them. And these anyons have various types, or various types. And I can also measure them somehow. Okay, so the topological part of this is, let's say we look at this, we stretch this out into time, so that we get some three-dimensional thing. Like, I have four anyons, they start out like this, and then these go like that, and this one goes around this one. So the point is that it doesn't matter if this one goes like this. They shouldn't make it go that far. So it doesn't matter. Okay. As long as at some point these switch. And this one doesn't go around like another angle. So basically what I'm saying is it really depends on the topological class of the braid. So these braids are going to correspond to computations. And that's the basic test.
Braids are going to correspond to gates, is that what you mean?
Yeah, yeah. Gates. Okay. So throughout the rest of this talk, I'm going to be talking about one specific type of anyon model, which is the Fibonacci anyon, which is somehow the simplest universal model. Okay, so here there are two types. This is going to be labeled by I and tau. And there's a fusion operation, which you're going to denote by O dot. So this is the trivial type. So fusing I with something doesn't change it. And then if I fuse a tau with a tau, then I get I plus tau. And what I mean by this is I'll get either an I or a tau, or it's like some superposition. That's how you should interpret your example. Okay. So now I'm going to describe. We can put all of this.
So you insist this.
No, it's not. Okay. So I should also write tau plus I.
That's
Yes.
Sorry, can I see, is I and tau, like mathematically, are those unit vectors? Is that
No.
what are they?
You should think of them as simple objects in a category. As objects. Or you should know.
Okay,
So
I'm-
vector
I'm-
spaces.
no,
Yeah,
what?
they're vector spaces.
Alright, so I'm just supposed to think of them as vector spaces.
Yeah.
Simple one.
Yeah.
Okay.
And then this fusion should you should think of it as like the tensor product,
Okay.
for example.
Okay.
As which product? Sorry?
The tensor product. we can make this into a category, which is going to be, it's going to be braided. I'm going to wait a little. Like a simple. And in fact, it's going to be a modular tensor category, but I'm not going to describe what that is. So everything's going to take place over C here. So this is the tensor product.
McGill, what is needs to be done?
So this is the tensor product. And it has and these equations here hold. And it's possible to solve for the associativity and braiding work stems by solving like the pentagon and hexagon equations. But we're not going to get into that, and instead we're going to describe another way to get this category, which is through quantum groups. Okay, so an important question is, where are the qubits? Since I'm claiming that this is quantum computing. So let's say, so this distributes. So suppose we want to compute what we get when we fuse three things outside tau. So then so this is the result, and so how you should interpret this again is you can either get tau, which happens in two different ways. So either you could choose these and get a 1 and then get a tau, or you could use these and get a tau and then get a tau. Or you could do this and then get a 1 or an idea. Okay. So basically, the first way to get tau is going to correspond to this vector. And this is going to correspond to this. And this is going to be nothing, basically. Like this is a state we compute with. So another way of writing that.
So what's the answer to the question, where are the qubits?
Yeah, that's what I'm going to say. So where the qubits are is they live here. This is C2. And then you can think of the first fusion possibility as 0, and the second fusion possibility as 1. That's the cat 0. Okay. And then the way you can imagine measuring these qubits is you would fuse the first two, and if you get a 1 here, and then you get a tau at the end, you get this. And then if this happens, then it means that something has gone horribly wrong, and you should start over, basically. And look, it turns out that, so one of the challenges is to make sure that things like this don't happen too often. Okay. So now I'm going to talk about quantum groups. So quantum groups aren't groups, which is a good first thing to know. They're algebras. And the basic setup here to keep in mind is that quantum groups are going to give us adversity. Okay. I'll try to fix it. So quantum groups are going to give us analog models. Their irreducible representations, roughly, are going to give us the different types. And then tensor products of the ERFs is going to give us fusion. And the braiding in the category of representation is going to give us exchanging, the operation of exchanging anions. So we can get the Fibonacci anion from a particular quantum group, which is a huge deformation of the universal enveloping algebra of SL2. So I'm going to try to explain what that is in some of the computer right now. So okay. So SL2, or its universal enveloping algebra, is an algebra. This is an algebra, and it's generated by x, y, and h with these relations. And this deformation. So here Q is a complex number, which doesn't square to 1. And this is generated by some things. So these equations are exactly what we too important to us for now. But I want to show you the relation between this and this.
Yeah, don't stand in front of them.
Okay.
Concealing them from you.
Okay. So you can see in these equations, if you send e to x and l to y and l to h and k to 1, then this just reduces to that.
Q to 1 as well.
Yeah, sorry. And you said k to 1. So then, if we set q equal to 1, which isn't a lot, but if we do that, then we get that.
Julia?
Yeah?
What, X, Y, and H are assumed to be in SL2? on the left side, are they assumed to be in SL2?
So here they're just abstract generators.
Okay, so I don't see what it has to do with SL2.
So these are the defining relations of SL2?
Okay,
That's the algebra of SL2, it's exactly right.
Yeah,
so those kind of
Those
things,
three.
if you take any elements to
Yeah.
satisfy and you'll get to SL2.
I mean SL2 is the Lie algebra.
yeah. Okay, okay.
Yeah. Okay, so this is a sketch of what it means that this is a deformation, right? If you set Q equals 1 and quotient by K minus 1, you just get the universal enveloping algebra, the Lie algebra, SL2 back. So, to further convince you that this has something to do with SL2, and because we're going to need some of the representation theory, I'm going to quickly sketch what the representation theory of this looks like when Q is not a root of unity. And it turns out that the representation theory of this looks very much like the representation theory of this. Which is kind of comforting. Okay. So, in SL2, we have here Vn for each integer n greater than 0, right? And then, yeah.
Can you write figures?
Yeah.
Firmer?
And speak louder. And look at us.
Thank you.
Double next slide.
Okay. So the way x, y, and h act is they basically either step you down or step you up, right? So vi goes to vi is 1 plus some coefficient. And then these are the arguments of h. So over here, the situation is more or less similar. Here we're assuming that Q is not a root of unity.
Yeah, sorry, Julie, can I ask you something? It's just for intuition. So you said the U on the left,
Yeah.
right, like the simple one,
Yeah.
that was the enveloping algebra of SL2. And so the one on the right, like where does it come from, or why would somebody write it down, or who wrote it down? I'm kind of mystified by it. Like
Grinfeld.
Okay. Enveloping algebra is much bigger.
Sorry?
Enveloping algebra is much bigger.
UQ?
No, without the Q.
UQ is the one I'm asking about.
UQ,
UQ,
that is Grinfeld. One second.
Yeah.
You got it out by black magic.
I mean, okay, is that it?
No, one can give explanations of after the fact, but in fact we did produce it by black magic.
Okay,
So we're amazed we don't know things like it.
okay, well, yeah.
So in Q's not a unity, things are kind of nice. We have spin plus or minus, so there's 2 of them for each n. And these are the same kind of So instead of being eigenvectors of H, they're eigenvectors of K. But over here, we replace the integers with Q integers. So these Q integers are defined like this. And they show up like all over the place. For reasons that are still slightly mysterious to me. If someone could explain it to you, it would be amazing. So if Q equals 1, then the Q integer n is just n.
It's just a definition.
Yeah, this is just the definition.
This was from 19th century.
Alright.
Weird guys started writing this stuff down. Ramanujan was one of the people who liked this stuff.
That says, sorry, what does it say on the bottom? That doesn't say Q minus Q inverse. Does it?
Yeah.
Q minus Q inverse.
Okay.
This is just a Q to the n minus 1.
I guess Q is not allowed to be 1, you just force
Yeah.
it to be.
Yeah, exactly.
Right.
I said that at the beginning.
Or minus 1.
No, but it has a limit. If you like,
Oh,
you use not the part.
Yeah.
okay.
Then it's also going to go.
Well, yes, as Q tends to 1,
Yeah.
till C tends to n.
Okay, that's good. That's
Or if you rewrite it like this, then you can define it for Q equals 1. Also. So when Q is not a big or to be big, everything is great and the representation theory is nice, but we're not interested in it actually. Because we want the case when Q is root of infinity. And then what happens is we get, these are some of the simple reps, and then there's a whole bunch of, like there's an uncountable class of simple reps, which all have the same dimension, and it's a bit of a mess. So what I want to do now is talk about how we clean it up, like how we clean up the category of representations.
So you can understand what was unclean about it.
There's too much stuff. We want to end up with a finite amount of simple logics, and we want the category to be semi-simple. So if Q is root of infinity, then the category of reps becomes semi-simple. Okay. So let's talk a bit about the structure of the category of finite dimensional representations of this. So I'm going to abbreviate this to UQ. This is an algebra. So we would like there to be a tensor product. We need a tensor product. And the tensor product of two representations isn't necessarily a representation.
Tensor product of 3D schools that would necessarily be ABC.
No.
You can have things that are reps whose tensor product is not. But I thought this was a category of reps.
Yeah, but I'm showing you that the category is monoidal.
I don't understand. So I thought you start out with the category of reps, right? So everything in it is a rep.
Yeah.
So then how can the tensor product of two reps fail to be a rep?
If the category, like the tensor product is a vector space. I mean,
A tensor product may not be defined, right? But if a tensor product is defined,
yeah.
it's obviously taking reps to reps.
I mean, if you have D and W as vector spaces which are reps, there might not be a natural way to make V tensor W a representation.
But in general, it will be a representation, but not be irreducible.
Yeah, that's what it takes. You might have two irreps, and when you tensor them, there's no reason why the result is an irrep. But I can't understand how you can take two reps, tensor them, and fail to get a
Okay,
rep.
so let's say I have two reps, V and W, UQ. Next one A. And I want to say this is how A acts on B tensor W. Right? So how do I do it?
I don't know, you tell me.
I mean, so all I'm trying to say is that it's not trivial.
No, it's not trivial. You have to show that the category is monoidal.
Yeah, that's what I'm doing. That's the point.
Right. But I wouldn't start out by saying the tensor product may not be a rep.
Okay.
You might say,
Actually,
I
I
don't
the
know how to
category
define
may
it.
not be monoidal.
Ah, okay, to say that.
Okay, so the category may not be monoidal.
You're going to show us that it is.
Hmm?
But now you're going to show us that it is.
Yes.
Very good.
Proper mathematics, the verbs may not be true, but they are true.
Okay. So the way I'm going to show that the category is monoidal is I'm going to introduce a co-multiplication from U cube to U cube tensor U cube. So this gives us tensor, and then that epsilon called co-unit is going to give us tensor unit. And the way this works is more or less as you could guess. So AX1 B tensor W via and then for the unit okay. So for this to work, we need this and this to be mapped, to be algebra maps.
Which?
The co-multiplication and the co-unit need to be algebra maps. So in other words, this needs to be a bialgebra. And a bialgebra is exactly an algebra with a co-multiplication and a co-unit, such that these are not algebra. And yeah.
Do you have a reason why the co-unit also has to be an algebra map? Because if you consider the co-unit as a state on this thing, then that means that the state is statistically uncorrelated, and that's something you don't want to have in physics. Because it factors over products, yeah?
Can you say that again?
So if the co-unit is an algebra morphism, then the co-unit of a product is the product of the co-units applied to that. So if I look at A and B as random variables, that means they are uncorrelated. And if I look at the co-unit as a sort of state, and that's something you possibly don't have. I know that everybody is doing this, but I'm not convinced it's the right way.
What do you think? So does it help that states so these representations aren't sets of states?
No, the co-unit is a vacuum state of this thing.
Isn't what?
It's the vacuum state of this thing.
Yeah.
So why should that be uncorrelated? So sorry, just go ahead.
Okay, I don't know. point here is that the category of reps of any bialgebra is a monoidal category. So we'd also like to be able to take dual objects. Or we want our category to be rigid. So the way we do this for representations of a group I want to say something else first. I want to actually define these maps, just so that we have an idea of what they look like. So in, say in SL2, X acts on a tensor product by and another way of saying this is that this multiplication takes X to X tensor 1 plus 1 tensor. And in our quantum group, we're going to do something similar.
Julia, some symbols there, there's an N and a 1, but are they meant to be there or are they
No.
just left over?
Yeah.
Yeah. Okay.
Didn't get it properly there. Thanks. Okay. So here we have something which looks somewhat similar, right? Instead of having G tensor 1 plus, this should be plus 1 tensor E. We have some extra K's scattered around. Okay. So to make the category rigid,
What is rigid mean?
it has joules, more or less. So to get joules in for a group vector, if I have, say, then I find the action G like this, so I have the imply of G inverse C. So over here we don't have a notation of an inverse. So we're going to do something analogous. So you're going to find out F such that, which has to satisfy some conditions, which I'm not going to write down here. particular, it acts like an inverse in some way. That's going to be identity. And then we can define this. And then we can define this in more or less the same way.
Excuse me?
That's what we're doing.
If Q is the root of unity, are you sure that you still have S square equals identity? Is that still true?
Yeah.
Yes.
It follows from the definition which I haven't given you. Okay. So a bialgebra the bialgebra component is called top algebra. So really all I'm trying to say here is the representations, the category representations of Hopf algebra has duals and so it's rigid and monoidal. And this is, I think, a good motivation for the definition, for the definition of Hopf algebra. So we also need braiding, which I'm not going to get into too much right now. What needs to be done is we need to define some elements are and this has to satisfy, so let's say R is the sum of SI, then we can define R12 and 13. R2 very basic for SI in the first place, and TI in the first place. And this needs to satisfy basically the antibacterial equation. So
You need another crossing on 1, 2.
a 1, 2?
Yeah?
Okay. Right, thanks. So R1, 2, R
2, 3.
2, 3, R1, 2.
2, 3
Right. Yeah. Okay. So basically, this is defined such that if we take U tensor V to arguments U tensor U, then we end up with the braiding.
What's sigma UV?
It's defined like this.
What's the definition of
Here's the
sigma?
definition.
Well, the sigma is the ordinary switch of the tensor.
No, that would be the symmetric.
Yeah.
Yeah, it is.
So this is just some.
So it's a switch, and then you also apply R.
So R does no switch. R is just an endomorphism
Yeah,
of the
exactly.
tensor power, and you need to do this.
Well, R is just an element of U tensor U.
So the braiding is actually R composed with sigma.
Yeah, exactly. Exactly. Okay. So, if we have all of the structure on our category, then we can kind of fix the categorical representation. So we can define a trace. Which is called the quantum trace. Using all of these things. And what it turns out to be is the quantum trace is F is the regular trace of KF. Where K is one of the generators that we defined earlier. And then similarly we can find the quantum dimension.
Fighting for.
We can find the quantum dimension to do this. Trace of the energy times.
What's F? What's K? What's little f?
For any endomorphism.
I don't understand this whole way.
This one? Okay. So I'm defining the trace of an endomorphism F to be the trace of K. So K is an element of, right? A particular element of K's capital A. So
There is no constant.
it's the lower range. Is that better?
Yes.
I need to fix that box. Okay. Right. So what we're going to do, or the goal, is to get rid of the stuff with quantum dimension 0, basically. So an issue is that it turns out that there are some so basically
So having work.
basically there are representations which have quantum dimension 0, or which have direct semantics which don't apply. So to fix this, we're going to and I'm going to be fairly vague here. We're going to restrict our attention to a subcategory of kind of nice modulars. So,
Sorry, dude, can I ask you,
sure.
do you still have the same additive formula for dimensions? So is the quantum dimension of the plus the same as the sum of the quantum dimensions of the W?
No,
No. Just trying to,
otherwise that couldn't possibly happen.
Yeah, we could.
why,
And
why couldn't it happen?
the dimensions are,
The dimensions can be negative.
yeah.
Yeah.
Could happen. So is it additive?
The quantum phase is ordinary phase, so it is additive on the sum and multiplicative of the other phases. The whole point to define this quantum phase.
Yes, the answer is yes.
Yeah. With that, and you can have negative dimensions.
You can.
You can have negative dimensions, yeah. Seven or ten? Okay, cool. That's good. So I'm gonna quickly sketch the rest of what's going on and say how this relates back to Computation, which is where we started. So there's a guard edge to some nice graphs. Or the tilting modules, which is what they're called. And then,
So the subcategory, looking at the subcategory.
Yeah.
Yeah.
through restriction to the subcategory of tilting modules. And then we push in that subcategory. By the negligible morphism, which
What does negligible mean?
I'm going to tell you. So, so basically the result of this is that we're left with only things which have non-zero dimensions. So, here the category. So here let's say Q is proven L through unity and L is some other thing happen. Here some minor change. You end up with these simple objects, which are, so these BI plus are the representation that defined before. And the fusion rules are more, basically they're the fusion rules for SL2. So in SL2 we have the M.
possibly should not be larger than L. So it should be bounded by L somehow.
Yeah, exactly. So it should be bounded by
L minus K plus even number less or equal to L. Because it's the largest number which fits into the
yeah.
box.
And then I should be less than 2 times L minus 4. So you stop at 2L minus 2 minus F%. Right, so this is the bound. So in the particular case we're interested in, this is the last thing I'm going to say. So we have
Hiding.
so so normally we would have 2 plus 2 is 4, so we would have D4. But there is none. We have to fill up there.
So this is straight cutoff? By that
No.
bound? No. It's more than that.
Because so we have to cut off at 2 times here. L is 5, so L minus 2 is 3. So we have to cut off at 6 minus 3 plus 3 is 0. So this is just 0. And similarly, 1. And then, so B0 and B3 are going to like 1, and B2 and B1. So you can see that here this is the same. Tau after tau is 1, essentially. Yes, 100%.
Right?
Other remarks?
No, okay.
Well, thanks. So, questions?
Yeah. I have a question about when you wrote down what it meant for when you wrote down what a 0 and 1 were states. So can you? I have 2 questions actually. Can you write those down in symbols, and how do you write down a superposition of the states?
What do you mean by symbol?
Well, I mean, do you have to, every time you want to write down a 0 or 1, do you have to write it down in like that tree form that you wrote it down in?
No, well you can say it's an element of this Helm set, right?
Okay.
Tau to tau O.3.
Okay. And yeah, how do you write down a superposition of?
You can just write it down as a vector, right? So this is C2. So you can just write down an element of this and work with it.
Okay, I guess I don't know what the elements on the left.
So the elements of this isomorphism, they're basically these diagrams, right? Or
Okay.
they have a basis of these diagrams.
Okay.
That's how I represent them.
But they are, you can see them as vectors.
Yeah, you can see them as vectors, yeah.
That is a vector space.
Yeah, this is a vector space.
Okay.
And you can think of a basis for this vector space being these two diagrams.
Do you want the physical picture? Is that what you were asking? Or the mathematical picture?
Well, yeah, I'm in the mathematical picture, but it's kind of hard for me to see how. I guess I don't know.
You'd like to see them written down as matrices, right?
Sure. I mean, that was.
I mean, this is a vector space.
And can you do any number of qubits in this same way?
Yeah,
So does it turn into something like, you get in
right.
n plus?
So you would take a bunch of triplets, right? So this would be one qubit. And then this is a loop. And then this triple. And the way I can act on them is by conforming. Right.
That's the whole point of having qubits.
So 3 qubits would be 3 triples.
Okay.
Yeah. And the big issue is that at the end, so at the end I would measure this and see what I get, right, in each case. But by braiding between them, I might get out of my computational space. So I might end up measuring a 1 at the end and not a tau. And then I'd have to throw the computation away. So one of the challenges is to write down braids which don't take you too far out of the actual computation space.
Can you say a few sentences about the modularity of this category, or Q is the root of it?
Right. So this category is modular.
I asked for more than one sentence.
So basically what it means to be modular is it's kind of the opposite of being symmetric. So a symmetric category is where so is sigma UV equal to sigma DU. Right? So if I bring x twice, I just get the empty. And I can define something called the symmetric center. To be so somehow the objects just commute with all the other objects. And if this is trivial, then the category is modular.
That's like the center of the category.
Yeah, so yeah, if the category has trivial center, so it only consists of the identity, the unit, and tensor of the unit, then the category is modular.
And this one is modular why?
It's complicated. Yeah. But it's possible to prove. It's complicated. Are there more questions?
Why is it called Fibonacci?
Oh, good question. Yeah, that's easy. So,
Not
I said
invented
that.
by Fibonacci.
Tau times tau is 1 plus tau. Tau times tau. So tau is 2 tau plus 1. And if you keep on computing these, if this is 3 tau plus 2, by tau plus 3.
That's because of the golden ratio of the two.
And this is easy enough to check, right? Because if I multiply this by tau, I get a 3 tau here and a 5 tau plus 5 here. So then I get 8 tau and then 5.
Okay, any other questions? So let's thank everybody. Okay, so let's begin again.
Quick as up, I guess. How do you do this?